The morning of June 24, 1944, somewhere over the rolling farmland northeast of Munich, Oberleutnant Hans Weik pushed his Messerschmitt Bf 109 Gustav into a steep diving turn, the altimeter unwinding rapidly as he fled toward the sanctuary of lower altitude. Behind him, two silver shapes with distinctive twin booms grew larger in his rearview mirror. P-38, Lightnings from the 15th Air Force, climbing out of Italy on yet another bomber escort mission deep into the Reich. Weik had faced American fighters before. He knew their capabilities, their limitations, their predictable tactics. The twin-engined Lockheed fighters were formidable at altitude, with their turbocharged Allison engines and concentrated nose armament, but they possessed a fatal weakness that every Luftwaffe pilot had learned to exploit since the Lightnings first appeared over Europe in late 1943. Push into a steep dive beyond 420 miles per hour, and the P-38's controls would lock up. Its tail would begin violent buffeting, and the pilot would face an impossible choice between staying with an uncontrollable aircraft or bailing out if altitude permitted. Weik had used this tactic successfully 3 times before. The technique was simple, reliable, and had been disseminated throughout fighter units across Germany through official tactical bulletins. When engaged by Lightnings at a disadvantage, execute a split S or steep diving turn, accelerate beyond 450 miles per hour indicated airspeed, and the Americans would break off pursuit rather than risk the compressibility problems that had already killed dozens of their pilots in unrecoverable high-speed dives. His airspeed indicator climbed steadily, 380 miles per hour, 400, 420. The Messerschmitt remained controllable, responsive, stable. At 450 miles per hour, Weik began his recovery, pulling back gradually on the control column, feeling the G-forces build as his fighter transitioned from dive to level flight. He glanced back, expecting to see the Lightnings breaking away, climbing back to rejoin their bomber formation, abandoning the chase as they always did. Instead, the 2 P-38s remained locked on his tail, accelerating through the dive, closing the distance, their pilots showing no indication whatsoever of breaking off. For a moment, Weik wondered if he was facing inexperienced American pilots who didn't understand their aircraft's limitations, fools who would kill themselves trying to follow him into the compressibility envelope that would lock their controls and send them into an unrecoverable dive. Then the first burst of 50 caliber machine gun fire tore through his left wing, and Hans Weik realized with dawning horror that something fundamental had changed about the P-38 Lightning, and the tactical assumptions that had kept him alive for 18 months of combat over the Reich were no longer valid. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how the Lockheed P-38 Lightning transformed from a fighter that German pilots could reliably escape through diving maneuvers into a high-speed predator capable of matching or exceeding the dive. Performance of Germany's most advanced piston-engine fighters begins not with a single engagement, but with a fundamental aerodynamic problem that nearly killed the aircraft's operational viability before the United States entered World War II. When the United States Army Air Corps issued Circular Proposal X608 in February of 1937, calling for a twin-engine, high-altitude interceptor capable of reaching 400 miles per hour at 20,000 feet, they were asking for performance that pushed well beyond the boundaries of contemporary aerodynamic knowledge. Lockheed's chief engineer, Clarence Kelly Johnson, responded with a radical design that placed the pilot and armament in a central nacelle pod, flanked by twin booms, housing Allison V-17-10 engines and connecting to a shared horizontal stabilizer. The configuration offered significant advantages. All armament concentrated in the nose eliminated the convergence problems associated with wing-mounted guns. The pilot sat behind substantial armor protection with unobstructed forward visibility. Twin engines provided redundancy over vast ocean distances. Counter-rotating propellers eliminated torque effects during takeoff and landing. The twin-boom layout positioned the tail surfaces outside the propeller slipstream, reducing structural loads and vibration. But this innovative design also created aerodynamic characteristics that would prove nearly fatal when pilots pushed the Lightning into the high-speed diving maneuvers that tactical combat demanded. The problem emerged during test flights in 1941, long before the P-38 entered operational service, when pilots discovered that at speeds approaching 680 miles per hour, true airspeed at altitude, roughly Mach 0.68, the aircraft would enter a condition that engineers initially struggled to understand or explain. During these high-speed dives, the Lightning's tail would begin shaking violently. The nose would tuck under, steepening the dive angle further. The control column would become immovable, as if embedded in concrete, regardless of how much strength the pilot applied. The aircraft would continue accelerating downward in an increasingly steep trajectory, the controls completely locked, leaving the pilot with no ability to arrest the dive or reduce the descent rate. The phenomenon was called compressibility tuck, though the pilots who experienced it used more colorful and desperate terminology. In May of 1941, Army Air Corps Major Sina Gilkey encountered the problem while testing a YP-38 at 30,000 feet. His dive steepened beyond vertical, the controls locked solid, and for nearly 20,000 feet Gilkey rode the fighter downward, unable to bail out at those speeds, unable to recover, simply waiting to see if the aircraft would tear itself apart or impact the ground. As the Lightning descended into denser air at lower altitude, the compressibility effects gradually diminished. The controls slowly regained some responsiveness. Gilkey managed to recover using elevator trim, pulling out at dangerously low altitude after experiencing a phenomenon that aviation engineers had never systematically studied. He survived, but Lockheed test pilot Ralph Verdun was not as fortunate. In November 1940, Verdun's YP-38 shed its tail structure during a high-speed dive, killing him instantly and making clear that compressibility was not merely a control problem, but a structural threat capable of destroying the aircraft. Kelly Johnson later recalled the frustration and urgency of those months. "I broke an ulcer over compressibility on the P-38 because we flew into a speed range where no one had ever been before, and we had difficulty convincing people that it wasn't the funny-looking airplane itself, but a fundamental physical problem. The issue stemmed from the basic physics of transonic flight. As an aircraft approaches the speed of sound, airflow over certain parts of the structure accelerates to supersonic speeds, even though the aircraft itself remains subsonic. On the P-38's wing, the junction between the center section and the engine nacelles created a constriction that acted like a venturi, accelerating local airflow. At 500 miles per hour indicated airspeed at 25,000 feet, the true airspeed approached 650 miles per hour, and the localized airflow at the wing fuselage junction could reach speeds close to Mach 1. When airflow reaches transonic speeds, shock waves form. These shock waves dramatically alter pressure distribution across the wing and tail surfaces, moving the center of lift rearward and creating a powerful nose-down pitching moment. The same shock waves cause flow separation over the control surfaces, rendering them ineffective. The faster the aircraft flies, the worse these effects become, creating a feedback loop where increased speed generates stronger nose-down moments that steepen the dive and increase speed further. Every aircraft eventually encounters compressibility effects if flown fast enough, but the P-38's specific configuration made it particularly vulnerable at speeds that combat operations routinely demanded. Unlike single-engine fighters where the fuselage provided a relatively smooth aerodynamic shape, the Lightning's twin-boom design created complex interference patterns. Unlike aircraft with conventional tail surfaces mounted on a single fuselage, the P-38's horizontal stabilizers connected the two booms in a configuration that experienced severe buffeting when shock waves formed on the wing center section. The problem was urgent because compressibility limitations directly threatened the Lightning's combat effectiveness. Diving attacks from altitude represented one of the most fundamental fighter tactics. A pilot who possessed altitude advantage could convert that potential energy into kinetic energy through a dive, using speed to close on enemy fighters or bombers, make a firing pass, and then extend away using that same speed before the enemy could react. If the P-38 could not safely dive beyond 420 miles per hour indicated airspeed without risking loss of control or structural failure, enemy pilots would quickly learn to exploit that limitation. They would dive away when engaged by Lightnings accelerating through the lightning's safe speed envelope into regions where the American pilot dare not follow. This would effectively neutralize many of the P-38's advantages in firepower, range, and high-altitude performance. Lockheed engineers worked throughout 1942 and 43 to understand and solve the compressibility problem. They conducted wind tunnel tests at the Ames Laboratory, operated by the National Advisory Committee for Aeronautics, using scale models to study airflow patterns at high speeds. They modified the wing fuselage fillets to improve airflow and reduce buffeting. They tested various aerodynamic solutions, seeking some way to delay shockwave formation or reduce its effects. The solution finally emerged in late 1943, not through preventing compressibility, but through providing pilots with a way to recover from it. Lockheed developed electrically actuated dive recovery flaps, small surfaces positioned on the underside of the wing just outboard of the engines. When deployed, these flaps extended 35 degrees in approximately 1.5 seconds, creating substantial additional lift on the outer wing panels. The dive flaps did not slow the aircraft significantly. Instead, they altered the pressure distribution across the wing, generating a nose-up pitching moment powerful enough to overcome the nose-down moment created by compressibility effects. With the dive flaps deployed, a pilot could maintain or regain control, even at speeds that would otherwise have locked the controls completely. The flaps allowed recovery from dives that would previously have been fatal. Testing proved the effectiveness of the modification. A United States Army Air Force's test pilot reported successfully diving a P-38 equipped with dive recovery flaps to an indicated airspeed of almost 600 miles per hour, recovering without difficulty. The actual true airspeed, after correction for compressibility error on the instruments themselves, was somewhat lower, but still represented a dramatic increase in safe diving speed compared to earlier Lightning models. By late 1943, Lockheed had prepared several hundred retrofit modification kits designed to add dive recovery flaps to P-38s already in operational service across the European, Mediterranean, and Pacific theaters. These kits would give Lightning squadrons immediate access to the improved dive performance without waiting for new aircraft to roll off the production line. However, logistics and military operations have a way of disrupting even the best plans. In March 1944, a Douglas C-54 Skymaster transport aircraft departed the United States carrying 200 dive flap modification kits destined for 8th Air Force P-38 squadrons operating from England. The kits would have immediately transformed the tactical capabilities of hundreds of Lightnings engaged in bomber escort missions over Germany, allowing American pilots to pursue diving German fighters that they had previously been forced to let escape. Somewhere over the Atlantic, a Royal Air Force fighter pilot on patrol spotted the C-54. From a distance, through cloud breaks, the four-engine transport's silhouette resembled that of the German Focke-Wulf FW-200 Condor, a long-range reconnaissance bomber that the RAF had standing orders to destroy on sight. The RAF pilot attacked, shooting down the Douglas transport and killing its crew. The 200 dive flap kits sank in the Atlantic, and the P-38 squadrons in England would have to wait months longer for the modification that could have saved pilots' lives and changed tactical outcomes. Meanwhile, back in Burbank, California, Lockheed continued producing P-38J models. Through the spring of 1944, newly manufactured fighters were towed from the assembly building out to the open ramp, where modification teams installed dive flaps in the late open air because production line integration had not yet been completed. The final 210 P-38J aircraft, designated J-25LO, finally received dive flaps as part of the standard assembly process in June of 1944. This 14-month delay between successful testing and full production implementation meant that only approximately half of all P-38s ever built received dive recovery flaps as original equipment. Thousands of Lightnings already in service would have to wait for retrofit kits, if they received them at all, or continue operating with the compressibility limitations that German pilots had learned to exploit systematically. The Luftwaffe's tactical understanding of the P-38's dive limitations had developed through combat experience during late 1943 and early 1944, German fighter pilots reported through intelligence channels that American twin-engine fighters with distinctive twin-boom configurations could be evaded reliably through steep diving maneuvers. Unlike the P-47 Thunderbolt, which could safely dive at speeds exceeding 500 miles per hour, and unlike the P-51 Mustang with its laminar flow wing optimized for high-speed performance, the Lightning demonstrated clear reluctance to follow German fighters into high-speed dives. This tactical intelligence was disseminated through Luftwaffe training schools and operational fighter units. Pilots learned that when engaged by P-38s at a disadvantage, the proper response was immediate dive. Maintaining the dive until achieving speeds beyond 450 miles per hour indicated airspeed, then recovering confident that the American fighters would break off rather than risk compressibility lockup. The tactic worked reliably throughout the winter of 1943 and into the spring of 1944. German pilots used it successfully to break contact, escape when outnumbered, or decline combat when tactical conditions were unfavorable. The P-38's compressibility limitations had become as much a part of Luftwaffe tactical doctrine as the Messerschmitt Bf 109's superior initial dive acceleration or the Focke-Wulf FW190's excellent roll rate. This tactical balance would shift dramatically during the summer of 1944 as P-38J-25 models with factory-installed dive flaps began arriving at operational squadrons, and as retrofit kits finally reached units flying earlier Lightning variants. German pilots who had grown accustomed to escaping through diving maneuvers would discover that their reliable tactical solution had suddenly become a fatal trap. The Messerschmitt Bf 109 that Hans Weik flew on that June morning represented the culmination of nearly a decade of continuous development and refinement. The Gustav series, introduced in 1942, equipped the majority of Luftwaffe fighter units by mid-1944. The aircraft possessed excellent climb rate, good acceleration, heavy armament, and handling characteristics that experienced pilots praised despite certain limitations. But the Bf 109 also had structural limitations that were well understood within the German aviation community, even if operational pilots sometimes exceeded them under combat stress or when survival demanded taking risks that peacetime test flying would never have accepted. The aircraft's dive speed limitations had been the subject of considerable analysis and documentation throughout the war years. Official Luftwaffe technical bulletins, issued in August 1942, specifically addressed dive speed limitations after a series of accidents attributed to structural failures during high-speed dives. The documents warned that maximum permissible airspeeds at various altitudes were not being observed and were being widely exceeded by operational pilots. At 11,000 meters altitude, the maximum dive speed was listed as 750 kilometers per hour. At lower altitudes, where air density increased and aerodynamic loads grew correspondingly higher, the limits were more restrictive. German test pilots had explored the Bf 109's high-speed dive characteristics systematically during 1943, using instrumented aircraft to measure exactly what happened when the fighter was pushed to and beyond its design limits. The tests used a Bf 109F airframe fitted with G-series wings, flown by multiple test pilots in carefully controlled conditions to minimize the risk that pilot error or overcorrection would confound the data. The aircraft achieved a maximum indicated airspeed of 737 km per hour at 4.5 km altitude, corresponding to a true airspeed of 906 km per hour. At 7,000 meters, the test aircraft reached Mach 0.805, the highest Mach number achieved by a Bf 109 in documented testing. These tests revealed that beyond approximately 650 km per hour indicated airspeed, the aircraft experienced oscillations around the yaw and longitudinal axes, beginning at the vertical stabilizer. The controls became extremely heavy. Violent buffeting would develop. Critically, to prevent catastrophic structural failure during these tests, the engineers had to limit aileron deflection to 50% of normal movement. Even with this restriction, test pilots reported that recovery required extraordinary physical effort, and the aircraft suffered measurable structural damage from the forces involved. One test aircraft experienced such severe stress that it was written off after being dived to Mach 0.83, though the pilot successfully recovered at low altitude. For operational pilots in combat, these test results translated into very real limitations. A Bf-10-9 pilot could safely dive faster than early model P-38s, which gave German fighters a tactical advantage throughout late 1943 and early 1944, but the Messerschmitt could not dive at the speeds that late-model Thunderbolts or Mustangs could achieve. More importantly, attempting to exceed the structural limits risked catastrophic failure, wings tearing off, tail structures failing, landing gear unexpectedly deploying, and ripping through the wing root structure. Finnish pilots flying Bf-109s reported the terror of high-speed combat dives where they pulled back on the control column with all their strength, convinced they were about to impact the ground, only barely recovering at dangerously low altitude because the heavy elevator forces at high speed were deliberately designed to protect the aircraft's structure from overstress. The Messerschmitt would break apart if pulled too hard during recovery from a high-speed dive, so the controls were made deliberately heavy to prevent pilots from inadvertently exceeding structural limits. This created a paradoxical situation. German pilots could use diving maneuvers to escape from early P-38s with near-total confidence, but if American fighters with better high-speed characteristics, like the P-47 or P-51, initiated the pursuit, the Messerschmitt pilot would find himself in an increasingly desperate situation. He could not dive fast enough to escape, and if he dove too fast, he risked structural failure or losing control authority needed for recovery. The summer of 1944 marked a critical transition in the air war over Europe. By June, Allied forces had established a firm foothold in Normandy following the D-Day invasion. Strategic bombing operations against German industry continued from both England and Italy, protected by increasing numbers of long-range escort fighters. The Luftwaffe faced overwhelming numerical disadvantages, chronic fuel shortages, and declining pilot quality as training programs were compressed to rush replacements to operational units experiencing catastrophic attrition rates. Within this larger strategic context, tactical developments in aircraft performance and pilot training could still influence daily combat outcomes, even if they could not alter the war's ultimate trajectory. The arrival of P-38 Lightnings, equipped with dive recovery flaps, represented one such tactical development, small in isolation but significant in its cumulative impact on operational effectiveness and pilot survivability. Hans Weik managed to escape that June engagement through violent evasive maneuvering at low altitude, using the Messerschmitt's superior roll rate and his intimate knowledge of local terrain to break visual contact with the American fighters. He landed at his base near Munich with 17 bullet holes in his aircraft, 3 in the wings and 14 in the fuselage, close enough to have been fatal if the American pilot's aim had been slightly more accurate. That evening, Weik filed a detailed combat report describing the encounter. His account joined dozens of similar reports flowing into Luftwaffe intelligence offices throughout June and July of 1944 from pilots across multiple fighter geschwaders. The pattern was consistent and deeply troubling. American P-38 Lightning fighters were no longer breaking off pursuit during high-speed dives. Pilots who had successfully used diving maneuvers to escape from Lightnings as recently as April or May now found themselves under sustained attack at speeds exceeding 450 miles per hour, indicated airspeed, speeds where every Luftwaffe pilot's tactical training had assured them the twin-engine American fighters could not operate safely. The implications rippled through German fighter units with remarkable speed. Within weeks, tactical bulletins were updated to reflect the changed reality. The P-38 Lightning could no longer be considered reliably escapable through diving maneuvers. Pilots who had counted on that tactic as a guaranteed survival technique now faced the realization that they would have to fight or attempt alternative escape routes that exposed them to different risks. The transformation was not universal or immediate. P-38J-25 models with factory-installed dive flaps first reached operational units in June 1944, and retrofit kits for earlier models arrived sporadically throughout the summer, depending on supply priorities and unit locations. 15th Air Force squadrons operating from Italy received priority for modifications, because their missions required extended flights over heavily defended Austrian and Romanian targets, where dive performance could mean the difference between successful engagement and losses that headquarters could not sustain. 8th Air Force units in England faced a different situation. By mid-1944, the majority of P-38 groups in England were transitioning to P-51 Mustangs, which offered superior range, lower cost, easier maintenance, and better high-altitude performance than even the improved Lightning models. The P-38 had proven valuable during the critical period when no other American fighter possessed adequate range to escort bombers deep into Germany, but the Mustang's arrival had fundamentally altered the strategic calculation. Lieutenant Colonel Jack Jenkins of the 55th Fighter Group led the first Allied fighters to reach Berlin on March 3, 1944, flying P-38H models without dive flaps. The mission demonstrated the Lightning's range capabilities, but also highlighted its limitations. German fighters engaged the escort at various points, and several pilots reported frustration at watching Messerschmitts and Focke-Wulfs escape through diving maneuvers that the Lightnings could not safely follow. By September 1944, all 8th Air Force Lightning groups except reconnaissance squadrons had converted to Mustangs. The 5 photo reconnaissance variant of the Lightning continued flying from England throughout the war, valued for its speed, altitude, performance, and ability to bring back critically damaged aircraft on a single engine. But for fighter escort and air superiority missions over Germany, the era of the P-38 in northwestern Europe had effectively ended. In the Mediterranean theatre, however, the Lightning remained operationally critical throughout 1944 and into 1945. The 1st, 14th, and 82nd Fighter Groups flew P-38s from Italian bases, escorting heavy bombers of the 15th Air Force on missions against oil refineries in Romania, aircraft factories in Austria, and transportation infrastructure throughout the Balkans. These missions required fighters capable of sustained high-altitude flight over distances exceeding 1,000 miles, and the P-38 remained ideally suited for this role. For these Mediterranean-based squadrons, the arrival of dive flaps represented a genuine tactical revolution. Pilots who had flown earlier Lightning models against experienced Luftwaffe fighters over Austria and southern Germany described the frustration of watching enemy aircraft escape through dives, forcing American pilots to choose between breaking off or risking compressibility problems that had killed squadron mates. With dive flaps, those same pilots could pursue diving German fighters with confidence, exploiting the Lightning's concentrated firepower and twin-engine survivability. The tactical transformation was not limited to pursuit situations. Dive bombing missions, which had always been problematic for early Lightnings due to dive speed limitations, became operationally feasible with dive flaps installed. On June 10, 1944, 46 P-38s from the 82nd Fighter Group conducted a dive bombing attack on the Romano-Americana oil refinery at Ploiești, Romania, one of the most heavily defended targets in Europe. Each Lightning carried a 1,000-pound bomb, releasing from 3,000 feet after diving from 7,000 feet. The mission achieved good bombing results, but at significant cost. 22 P-38s were lost in fighter combat and to anti-aircraft fire, against 23 German aircraft claimed destroyed. The losses were severe, but the mission demonstrated that Lightnings equipped with dive flaps could execute vertical dive bombing attacks that would have been suicidal for earlier models. The ability to dive steeply, release weapons accurately at low altitude, and recover with sufficient energy to engage defending fighters or extend away from the target area represented a fundamental expansion of the Lightning's operational flexibility. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. For German pilots defending against these improved Lightnings, the tactical situation deteriorated throughout the summer and fall of 1944. The challenges they faced extended far beyond the P-38's improved dive performance. By mid-year, the Luftwaffe confronted overwhelming numerical inferiority, chronic fuel shortages that limited training and operational sorties, declining pilot quality as experienced aviators were killed or captured faster than replacements could be trained, and deteriorating infrastructure as Allied bombing systematically destroyed aircraft factories, fuel production facilities, and transportation networks. Within this context of strategic collapse, individual aircraft performance characteristics mattered less than they might have earlier in the war. A Luftwaffe pilot who possessed superior training, adequate fuel, and a well-maintained aircraft could still achieve tactical successes against Allied fighters. But such advantages became increasingly rare as 1944 progressed. More commonly, German pilots found themselves outnumbered, flying aircraft with maintenance deficiencies, operating from bases under constant air attack, and struggling with fuel shortages that forced cancellation of training flights and limited combat sorties to the most critical missions. The improved P-38 dive performance removed one of the few reliable tactical advantages German pilots had retained. Combined with the growing presence of P-51 Mustangs with their exceptional range and high-speed performance, and P-47 Thunderbolts with their devastating diving attacks and ability to absorb tremendous battle damage, the Luftwaffe's fighter force faced opponents who possessed advantages in numbers, training, equipment quality, and tactical flexibility. German engineers and aircraft designers understood these challenges and worked desperately to develop fighters capable of overcoming Allied advantages through technological superiority. The Messerschmitt Me-262 jet fighter represented the most successful of these efforts, achieving speeds exceeding 540 miles per hour through revolutionary turbojet propulsion. However, the Me-262 suffered from chronic engine reliability problems, required extensive concrete runways vulnerable to Allied attack, consumed vast quantities of increasingly scarce fuel, and arrived too late in far too few numbers to influence strategic outcomes. Advanced piston engine fighters like the Focke-Wulf Ta-152 and the refined Bf-109K series offered improved high-altitude performance and better armament. But production problems, material shortages, and the deteriorating overall war situation prevented these types from entering service in numbers sufficient to challenge Allied air superiority. The handful that reached operational units demonstrated impressive capabilities, but could not overcome the fundamental imbalances in resources, production capacity, and trained personnel. The Pacific Theater presented a dramatically different operational environment where the P-38 Lightning achieved its greatest successes. The vast distances between bases, the extended overwater flights, and the lower altitude combat typical of the theater all favored the Lightning's specific characteristics. Twin engines provided insurance during hours-long missions, where a single engine failure hundreds of miles from base meant almost certain death. The concentrated nose armament allowed accurate, long-range gunnery. The high-altitude performance and range exceeded that of any Japanese fighter. Major Richard Bong and Major Thomas Maguire, the two highest-scoring American fighter aces of World War II, both flew P-38s exclusively in the Pacific, achieving 40 and 38 confirmed victories respectively. The Lightning destroyed more Japanese aircraft than any other American Army Air Force's fighter type, and more than 100 Lightning pilots achieved ace status by downing 5 or more enemy aircraft. In the Pacific, compressibility limitations affected operations less severely than in Europe. Combat typically occurred at lower altitudes where air density was higher and compressibility effects were less pronounced. Japanese fighters possessed excellent maneuverability, but could not match the Lightning's speed or diving acceleration. American pilots could engage using boom and zoom tactics, diving on enemy formations from altitude advantage, making firing passes, and extending away using superior speed before Japanese fighters could react effectively. The mission profile that exemplified the P-38's Pacific capabilities occurred on April 18, 1943, when 16 Lightnings from the 339th Fighter Squadron flew an 800-mile mission from Guadalcanal to intercept a flight carrying Admiral Isoroku Yamamoto, commander of the Japanese Combined Fleet, over Bougainville. The mission required precise navigation over open ocean, perfect timing, extended combat at low altitude, and sufficient fuel to return to base after engaging enemy fighters. Captain Thomas Lanphier and Lieutenant Rex Barber intercepted the two Betty bombers carrying Yamamoto and his staff, shooting down both despite determined defense by escorting 0 fighters. All 16 P-38s returned to base after completing a mission that would have been impossible for any other American fighter then available. The Lightning's range, twin-engine reliability, and concentrated firepower had enabled a strategic success that directly impacted Japanese naval operations for the remainder of the war. But this narrative focuses on the European theatre and the specific tactical evolution that occurred when the P-38 gained dive capabilities matching or exceeding those of its German opponents. The transformation was most visible in the 15th Air Force operating from Italy, where P-38 squadrons continued flying bomber escort and fighter bomber missions through the final year of the European War. By late summer 1944, German pilots had adjusted their tactics to account for the Lightning's improved dive performance. Rather than automatically diving to escape when engaged by P-38s, they now evaluated each situation more carefully. If outnumbered badly, diving might still offer the best escape route, gambling that some Lightning pilots might be flying earlier models without dive flaps or that confusion in combat might allow escape. If numbers were more equal, German pilots would attempt to engage using their aircraft's superior roll rate and acceleration advantages. The Bf 109 Gustav retained excellent initial acceleration in a dive due to its lower drag and smaller frontal area compared to the twin-engine Lightning. In the first few seconds of a diving maneuver, the Messerschmitt would pull away from a pursuing P-38. But, as both aircraft accelerated and speeds climbed above 400 miles per hour, the Lightning with dive flaps could maintain control and continue accelerating while the Messerschmitt approached its structural and aerodynamic limits. German pilots learned that successful evasion now required combining multiple maneuvers: initial dive to gain separation, then roll and reversal before the Lightning closed the distance, using terrain masking and aggressive maneuvering in the vertical plane to break the American pilot's tracking solution. These techniques required significant skill, excellent spatial awareness, and considerable luck. Less experienced pilots who attempted them often failed, either being shot down during the maneuver sequence or making mistakes that gave pursuing American fighters decisive advantage. The cumulative effect across hundreds of engagements during the summer and fall of 1944 was measurable. Lightning squadrons in the Mediterranean theatre reported increasing success ratios against German fighters. Pilots who had previously expressed frustration at watching damaged enemy aircraft escape through dives now reported successful pursuit and destruction of targets that would have escaped months earlier. Combat losses declined as American pilots could more confidently engage in the diving attacks that maximized the Lightning's advantages while minimizing exposure to enemy fire. For the Luftwaffe, each lost aircraft and each killed or captured pilot represented an irreplaceable loss. German fighter pilot training had been compressed from approximately 250 hours of flight time in 1940 to as little as 120 hours by late 1944. New pilots arriving at operational units lacked the experience and skill that their predecessors had possessed. They were more likely to make fatal mistakes, less able to extract themselves from dangerous situations, and more vulnerable to the tactical sophistication of increasingly confident American pilots who had survived long enough to develop genuine expertise. The strategic bombing campaign against German oil production facilities intensified throughout 1944, systematically destroying the fuel sources that powered the Luftwaffe's operations. By December, fuel shortages had become so severe that pilot training was essentially impossible. New fighters sat on airfields unable to fly because no fuel was available. Experienced pilots who might have trained replacements instead flew combat missions, where they faced overwhelming odds and eventually were killed or captured, taking their knowledge and experience with them. Within this broader context of Luftwaffe decline, the P-38's improved dive performance represented one component of accumulated advantages that made German fighter operations increasingly untenable. No single technological improvement or tactical innovation defeated the Luftwaffe. Rather, the cumulative weight of numerical superiority, better logistics, more thorough training, superior production capacity, and incremental technical improvements like dive recovery flaps combined to create an overwhelming imbalance that German skill and courage could not overcome. The final months of the European War witnessed the Luftwaffe's dissolution as an effective fighting force. By January 1945, fuel shortages limited operations to the most critical defensive missions. Allied fighters roamed over Germany with near impunity, attacking airfields, strafing transportation, and engaging in air combat when German fighters could be found. The few experienced Luftwaffe pilots still alive fought with remarkable determination despite hopeless odds, motivated by duty, defense of homeland, or simply the continuation of habits developed over years of combat. Lightning squadrons continued operations through April 1945, when organized German resistance in Italy collapsed. The 1st, 14th, and 82nd Fighter Groups flew their final combat missions escorting bombers against remaining German positions in northern Italy and Austria. By that point, aerial opposition had become sporadic and ineffective. More missions were scrubbed due to lack of targets than were flown against meaningful German resistance. The ultimate measure of the P-38's contribution to Allied victory extends beyond simple kill ratios or mission statistics. The Lightning provided long-range escort capability during the critical period of late 1943 and early 1944, when no other American fighter could effectively protect bombers over German industrial targets. The aircraft's twin-engine reliability saved countless pilots who would have been lost over water or enemy territory, flying single-engine types. The concentrated nose armament provided firepower that proved decisive in numerous engagements, and the dive recovery flaps, developed through systematic engineering to solve a fundamental aerodynamic problem, transformed the aircraft from one that German pilots could reliably escape through diving maneuvers into one that could pursue and destroy targets at speeds approaching 600 miles per hour. That transformation occurred relatively late in the Lightning's operational career and affected a limited portion of the aircraft produced, but for the pilots who flew those improved fighters, and for the German pilots who faced them, the change was profound and often fatal. Hans Weik survived his encounter with dive flap-equipped Lightnings in June 1944. He continued flying combat missions through November, when his Messerschmitt was damaged by P-51 Mustang fire during an engagement over Munich. He managed to crash land at his base, but sustained injuries that ended his combat flying career. Weik spent the final months of the war as a flight instructor, training replacement pilots who would never accumulate sufficient experience to become effective in combat before Germany's surrender in May 1945. After the war, Weik was interviewed by Allied intelligence officers, gathering information about German tactical doctrine and pilot perspectives on various Allied aircraft types. His assessment of the P-38 was nuanced and reflected the complex reality of air combat, where absolute statements about aircraft superiority rarely captured operational truth. The early Lightning, Weik explained, was a capable fighter with excellent firepower and good high-altitude performance, but it possessed exploitable weaknesses in dive performance and cold weather reliability that made it less threatening than the Mustang or Thunderbolt. The improved Lightning with dive recovery flaps eliminated the most significant tactical weakness, creating an aircraft that German pilots had to respect and could no longer reliably escape from through diving maneuvers. However, Weik emphasized, by the time improved Lightnings became common in mid-1944, the broader strategic situation had deteriorated so severely that individual aircraft capabilities mattered far less than they had earlier in the war. Fuel shortages, numerical inferiority, declining pilot quality, and collapsing infrastructure meant that even if the Luftwaffe had possessed superior fighters, which increasingly they did not, the overall imbalance would still have ensured defeat. This assessment, pragmatic and free of the propaganda that had characterized wartime pronouncements, reflected a truth that many German fighter pilots recognized during the final year of the war. They fought with professional competence and personal courage against opponents who possessed overwhelming advantages in virtually every dimension of military power. Individual tactical victories, moments of superior airmanship, or even better aircraft, could not overcome the fundamental imbalances that determined strategic outcomes. The story of the P-38, Lightning's transformation from a fighter limited by compressibility effects to one capable of high-speed diving combat, illustrates several principles that remained relevant long after World War II ended. First, technological problems that appear fundamental and potentially fatal can sometimes be solved through systematic engineering and testing. The compressibility issue that nearly killed the P-38 program was resolved not by redesigning the entire aircraft, but by adding relatively simple dive recovery flaps that changed airflow patterns sufficiently to provide control at high speeds. Second, operational limitations known to one side in a conflict will inevitably be exploited by the other side if given opportunity and time. German pilots learned about the early Lightning's dive limitations and incorporated that knowledge into tactical doctrine, using it successfully for months. When the limitation was eliminated through engineering improvements, German pilots had to adapt their tactics or face increased losses. Third, individual technical improvements occur within larger strategic contexts that ultimately determine their significance. The P-38's dive recovery flaps arrived at a time when Allied air superiority was already established through numerical advantages and improving pilot training. The flaps made the Lightning more effective, but they did not fundamentally alter strategic outcomes that were being determined by industrial capacity, resource availability, and the cumulative effects of years of sustained combat. The engineering challenges that Kelly Johnson and his team faced, developing the P-38, pushed aviation technology into new regions of performance, where aerodynamic phenomena poorly understood in the late 1930s became operationally critical. The solutions they developed, particularly the dive recovery flaps, represented pioneering work in high-speed aerodynamics that would inform post-war research into transonic and supersonic flight. The P-38 Lightning ended World War II with a mixed operational record that reflected both genuine capabilities and real limitations. In the Pacific, the Lightning achieved remarkable success, downing more enemy aircraft than any other American Army Air Forces fighter and proving ideally suited to the theater's specific operational requirements. In Europe, the Lightning served effectively during the critical period before longer-range alternatives became available, but was ultimately replaced by fighters better optimized for the European combat environment. The aircraft's distinctive twin-boom configuration, radical in 1937 when the design was finalized, proved both advantage and limitation. The configuration enabled concentrated nose armament and twin-engine reliability, but created complex aerodynamic behaviors that required years of development to fully understand and partially resolve. The compressibility problems never disappeared completely. Even with dive recovery flaps, the Lightning remained more susceptible to high-speed control difficulties than single-engine fighters with more conventional configurations. For the men who flew the Lightning in combat, evaluations of the aircraft depended heavily on theater, mission profile, and individual experience. Pacific pilots generally praised the fighter enthusiastically, valuing its range, reliability, and firepower for missions over vast ocean expanses. European pilots expressed more mixed opinions, with some loving the aircraft's capabilities while others found its size, complexity, and cold weather problems frustrating compared to the more nimble Mustang. German pilots who faced Lightnings in combat similarly expressed varied assessments. Early encounters often noted the Lightning's unusual appearance and heavy firepower, but also its exploitable dive limitations. Later assessments, after improved models appeared, showed increased respect for an aircraft that could no longer be reliably escaped and that possessed genuine advantages in specific tactical situations. The ultimate legacy of the P-38 Lightning extends beyond its direct combat record to its role in pushing aviation technology forward during a period of unprecedented rapid development. The aircraft demonstrated that twin-engine fighters could be effective, despite conventional wisdom favoring single-engine designs for fighter missions. It proved that concentrated nose armament provided significant advantages over wing-mounted guns, and it forced engineers to confront and partially solve aerodynamic problems that would have crippled the aircraft's operational viability if left unaddressed. The dive recovery flaps specifically represented an engineering solution that acknowledged physical limitations that could not be eliminated, while providing pilots with tools to operate safely within those limitations. This approach, accepting constraints while developing methods to work within them, would characterize much of the subsequent development of high-performance aircraft as aviation pushed toward and through the sound barrier in the late 1940s and 1950s. For Hans Weik, flying in increasingly desperate circumstances during the final year of the war, The P-38's evolution from escapable to dangerous opponent represented one more indication that Germany's tactical situation was deteriorating irreversibly. The dive tactic that had reliably saved his life 3 times during the spring of 1944 nearly killed him in June when the rules changed suddenly and dramatically. That experience, combined with countless similar experiences across the Luftwaffe's fighter force, illustrated that even experienced pilots operating from detailed tactical knowledge could find themselves overwhelmed when technology and circumstances shifted the foundations underlying their assumptions. The story concludes not with a dramatic final engagement but with gradual transitions as the war moved toward its inevitable end. Lightning squadrons continued flying missions through April 1945, encountering decreasing resistance as the Luftwaffe's operational capacity collapsed completely. German pilots who survived to see the war's end carried complex memories of aircraft they had faced, including respect for the twin-engine American fighter that had eliminated one of their few reliable escape tactics through systematic engineering and relentless operational pressure. In the decades following World War II, aviation museums around the world preserved P-38 Lightnings as examples of innovative wartime design. The distinctive twin-boom configuration remains instantly recognizable, symbolizing American engineering ambition during an era when aviation technology advanced with unprecedented speed. Several restored Lightnings fly today at airshows, demonstrating the performance that made the aircraft both challenging to fly and capable of remarkable achievements in the hands of skilled pilots. The dive recovery flaps, that crucial modification that transformed the Lightning's high-speed capabilities, are visible as small panels on the underside of the wings just outboard of the engine nacelles on these restored aircraft. Few spectators at modern airshows understand the significance of those panels or the engineering effort required to develop them. But for pilots who flew Lightnings in combat, and for German pilots who faced them, those simple flaps represented the difference between an aircraft with exploitable limitations and one that could pursue and destroy targets at speeds that would have been suicidal for earlier models. The tactical lesson remains relevant. Decades after the last P-38 flew in anger, known limitations will be exploited by capable opponents, and survival depends on either eliminating those limitations or developing alternative tactics that minimize their impact. The P-38 achieved both. First through dive recovery flaps that reduced compressibility problems, and later through tactical doctrines that emphasized the aircraft's advantages in firepower, range, and twin-engine survivability, while minimizing exposure to German fighters in situations where their advantages could be decisive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.